Hi guys, so this is our first video, and today is really just going to go back over everything that we did in class over the first day of content, which is a lot of characteristics of different functions. We'll look at domain, range, and behavior, increasing and decreasing intervals, relative extrema, and a lot of other things. So there's a lot of vocab in today's notes. So the first thing we're going to do is go over interval notation. That's probably a new one for you guys. So interval notation is a different way of showing an interval than something like inequality notation that you've seen before. The first thing we're going to do is we're going to look at some words that describe an interval, and then we're going to write that in all three forms. I'm also going to say what type of interval it is, because again, that is vocab that you're going to see in future math classes. So the first thing we're going to do, if it's all real numbers from A to B, including A and B, that is a bounded interval because we clearly know the start and stop point. In inequality notation, that would be our or equal to values. Set notation, if you notice, what follows after that bar is exactly what we did on inequality notation. And that little bar there just says, that's read as X belongs to the set of. Another thing you could see for inequality notation, or sorry, for set notation, you could see that X is an element of all real numbers. Then it follows that it belongs to the set A is less than or equal to X is less than or equal to B. So that X is an element of, that's something that you may see included. It's not something you'll have to include in this class, but as you go further, you may use set notation. Maybe you'll see that more often in a statistics class, or just something more down the road. Interval notation is the really important one. We're going to use that a ton this year, and you're going to use this a lot in your future math classes. So interval notation is typically going to be used with brackets and parentheses. It's a little bit more concise, I think, also to describe these things. What you need to remember for interval notation, parentheses mean the value is not included. Square brackets mean the value is included, and there's a note on that there at the bottom of your chart on your notes. So if I were to say the interval from A to B with A and B included, I would use those hard brackets. Our next interval, that is an unbounded interval. It is an infinite interval, and we would say that this is all real numbers greater than A, so X would have to be greater than A. That's inequality notation. Set notation, again, going to be very similar. X belongs to the set where X is greater than A. In interval notation, if it's everything greater than A, the smallest value is A, and I'm going to list that. Since it is not or equal to, I'm going to use a parenthesis, and then it's everything after, so I'm going to say it goes to infinity. Infinities and negative infinities will always have parentheses. All right, let's go to our next one. All real numbers less than or equal to A. So go ahead, pause it, try this one on your own. All right, so here, this would be an unbounded interval because it's all real numbers less than. We don't know a particular end. Inequality notation, X is less than or equal to. Set notation looks very similar. And then our interval notation, we have a bracket on the A, but we do not have a bracket on the negative infinity. And since, again, it's less than A, it's going to be from negative infinity until that value. So now we're going to switch over and we're going to look at a number line. This is going to help us get into graphs and domain and range. So here, remember a filled in circle. First of all, this is a bounded interval because we know the start and end points. In inequality notation, this would be -3 less than or equal to X is less than 4 because this is both the intersection of those two intervals there. Set notation, going to look very similar. And then interval notation. So the left number here is -3. It actually touches that -3, so it's going to be a hard bracket. Then it continues to 4. 4 is an open circle, so that's going to be a parenthesis. All right, so I want you guys to go ahead, pause it, try the next two on your own. All right, so that next example there, very similar to that third one that was written in words. This is all real numbers less than or equal to 3. So exactly the same, except instead of A, we're actually using the number 3, and this shows you the number line as opposed to giving you the values on there. Then this next one here, if you've already finished, this one is bounded. Both of these would be just less than, it would not be or equal to because they're open circles. Set notation is going to look very similar. And then interval notation here would both be parentheses because they are both open circles. Then the last one's going to be a little bit different. This is unbounded, actually on both ends. And this one is not continuous if this were to be a function. We'll talk more about that later. But if I want to write this in inequality form, what I'm going to do instead of writing as an inequality, I'm going to write this the simplest way possible. And I'm just going to say x is not equal to 4. Because that's just the simplest way that I could write this. Same thing here. I'm going to say x is not equal to 4. In interval notation, because there is that gap there and then your graph picks back up, the way we kind of show that gap is that we're actually going to have two intervals and they're going to be combined by the letter u for union. So this graph goes from negative infinity to 4. It does not touch 4, so I put a parenthesis. But then we're not done. There's still more to this number line. So then I'm going to say union to show that there's more. And then it's going to pick right back up exactly at 4. Because that means basically I'm getting as close to 4 as I possibly can get from both sides without actually touching it. So I can go to 3.9999999. I can go to 4.00001. But I can get as close to possible without actually touching. That's what the parenthesis shows us. All right, so now we're going to take interval notation and we're going to apply that to a graph. So on the video, I'm just going to go ahead and show you domain and range and interval notation. The copy of the notes online, you can see what inequality notation is. So first one, talking about domain. So when we're doing domain, domain is left to right. In interval notation, we're looking at our x values. So right here, the farthest left this graph goes is -3. The farthest right this graph goes is 5. So our domain is from -3 to 5. Because -3 is included, that is a hard bracket. Because 5 is not, that is a parenthesis. Then let's look at range. I'm going to make that a different color. So range is bottom to top. So I look at the lowest point on this graph. I do not necessarily look at anything relating to the x's. I only look at the bottom of my graph. The lowest y value on that graph is -1. The highest y value on that graph is 3. It does actually touch both of those points, so they are hard brackets. All right, example B. Let's pretend that these have arrows on them because they are actually continuing. So we'll start with domain. So left to right. The farthest left of this graph, that arrow is continuing to go to the left. So my domain here is going to be from -infinity. Then this is going to stop at this x value of -4. It does actually touch that point, so it's a hard bracket. Then it's nothing until we pick back up at 3. So I show that by saying union, parenthesis, 3, and then I keep going to infinity. All right, so now we look at range, bottom to top, and range here is a little bit different. Think about the entire graph. This graph is going to keep on going for forever. So my lowest range value is going to be -infinity. Even though it cuts off right here, that graph does continue on the right side and eventually will pass that point and will also keep going to infinity. So the range here on this function is from -infinity to infinity for all real numbers. All right, go ahead and pause it and try this for C. All right, so here is C. So the domain is actually from -infinity to infinity. Even though there are these gaps and these breaks, it doesn't matter because every x value is still included on this function. Same thing with range, as there's nothing below here, but this graph continues to infinity on this side. It doesn't matter that there's a gap there because those y values are still being touched by those other values. And then the last one here, again, let's go ahead and look at domain. Well, this arrow keeps going to the left, this arrow keeps going to the right, and there's no overlap here. It actually touches in both places, so my domain is from -infinity to infinity. Range, on the other hand, does have a defined stop point this time. So the lowest this graph goes is from -infinity until it gets to 0, at which point it touches 0, so I have a bracket. Then this graph picks back up again at 3, and continues to infinity, and that would be my range. Now, the one thing that makes this graph different than the others, this graph is the only one of those four that is not a function. So if you remember back from Algebra 1, a function was defined as long as it passed that vertical line test. No x is repeated. There's exactly one input for your outputs. So if you have any x values that repeat, your graph is not a function. The rest of these may not be continuous. Well, at least B and C are not continuous, but they are actually functions. D is the case where it's not. All right, so now we're going to move on to something called end behavior. End behavior is going to start to introduce you to the idea of a limit. So end behavior is just asking as my x's keep going towards the farthest end possible, what are my y's doing? So what I would do here on this first one, I'm going to look at both ends of my graph. So one end of my graph is as x approaches negative infinity. So as x approaches negative infinity, I need to see what my y's are doing. So as my x's approach negative infinity, that is the left side of my graph. So as my x's keep getting smaller, my y's are getting bigger, which means my y's are approaching positive infinity. Then we look at the right side of my graph. So as x approaches positive infinity, I look and see what my y's are doing. So the right side of my graph, there's that arrow. Well, that arrow is going down. So as x approaches positive infinity, y's are approaching negative infinity. All right, so go ahead and pause it and try B. All right, so as x approaches negative infinity, that is the left side of my graph. That left arrow is going down, which means the y's are approaching negative infinity. Positive infinity is the right arrow. The right arrow is also going down, so those are both approaching negative infinity. Now, it does not have to approach infinity or negative infinity, so C is going to be an example of that. So again, we're still going to look at both scenarios as x approaches negative infinity. That means the far left of that graph. So the far left of this graph, as my x's are going towards negative infinity, my y's are getting closer and closer to this value right here, which has a y value of 0. That's actually approaching something called an asymptote that we're going to see actually a lot in a couple different functions this year. All right, but then again, that's not for the whole graph. If you look at the right side of your graph, as x approaches infinity, y is approaching positive infinity because it is continuing to get larger. So while a lot of these end behaviors will be positive or negative infinity, it is possible for your graph to approach an actual value if there's an asymptote. So let's go ahead and look at D. You can go ahead and pause it and try that one if you want. So here, as x approaches negative infinity, we look at my y's. So the x's, as they get smaller and smaller, are getting closer and closer to that dotted line, which is that asymptote. That asymptote has a y value of 3. Then we look at the other side. Same thing, that y is also approaching that asymptote, which has a value of 3. Now, if you look at this little middle section, some people want to talk about that with end behavior. You will talk about that when you talk about limits, especially in either pre-cal or calculus. But because we would actually look at a different one side of that point, and it wouldn't actually be the end of our graph, we're not going to deal with it in here yet because we're not talking about end behavior. Well, your graph has a trend towards positive or negative infinity. It is not the end of our graph, so it's not going to go with our end behavior. All right, so the next new piece of vocab for you guys are our relative or absolute extrema. So there are two words that are going to be used interchangeably. Relative and local, you're going to see used interchangeably. I typically say relative more often, but I think on a lot of your assignments you'll see local more often. So a local or relative max or min. What that means, it's the highest or lowest points relative to the points around it. It's where your graph changes from increasing to decreasing. So your graph changes from, that's where it changes from increasing to decreasing, or the opposite way, but basically whether it's increasing or decreasing changes at one of these points. All right, so that's your relative or local max or min. And again, it's just relative to the points closest to it. It looks kind of like one of those turning points on your graph. What we'll also find on our graphs are the global or absolute maximum or minimum. Now, this may not exist for that function. It depends what type of a graph it is. But this is the highest or lowest point on the entire function. Typically, some graphs will have one of these, some graphs will not have any. So let's go ahead and find a few of these points. So this point right here, this is one you're used to finding. That is your global or absolute minimum. It is the absolute lowest point on the entire graph. But then we have two more of these turning points where your graph changes from increasing to decreasing. Those are relative extrema. One of those is a relative maximum or local maximum, and then one of them is a relative or local minimum, because it's the lowest point relative to the points around it. The relative maximum is the highest point relative to those near it. It's not the highest point in the entire graph, but it's the highest point of all of the points on either side of it. All right, so another example. This graph has two relative extrema or local. There is a relative or local max, and there is a relative or local min. There is not an absolute or global max or min on this graph because this graph keeps going in both directions. Now, probably the biggest mistake some people make when it comes to these is this center point right there. That is not a local or relative maximum or minimum because your graph is still decreasing through that entire interval. What that point actually is something called a point of inflection, which we will talk about here in a little bit. All right, so let's look at this last one. Go ahead, pause it, and try to do this one on your own. All right, so on this graph, you have kind of one of everything. Even though this point here on the end is an endpoint, it is still a relative minimum because it is still the lowest point relative to all those points near it. It doesn't matter that there's nothing over here. It's still the lowest point out of those points that are close to it. Then we've got a relative maximum at the top. We do have a global minimum that is the lowest point on the entire graph. We also, because this graph is bounded, we also have a global maximum. Now, an unbounded function, you're not going to have both of those. But since this is bounded, we definitively know the start and the end, and it's on that closed interval, then we do actually have both of them. Now, the biggest thing to be careful when it comes to local and global maxes and minimums is to consider and make sure you read your directions carefully. Now, the information you need about this right now, we're labeling a picture. But if you were to be given a question about one of these, it's important to understand the difference between where it is located and what the value of that minimum or maximum actually is. If it asked you where these things occur, that's when we're talking about the x-coordinate. If it's asking what the actual value is, that's when we're talking about the y-coordinates. All right, so our next little section, we just talked about this briefly, increasing and decreasing intervals. But since we're talking about intervals, we're also going to look at positive and negative. So whenever you see a question referring to intervals, we think interval notation. But instead of thinking of domain and range, we're just talking about the x values. And I accidentally skipped ahead. So intervals here, all right, where it's increasing, we're trying to find the x values where that is happening. And we're going to list those in interval notation. So on this first one, where this graph is increasing, would be this section right here. To list that in interval notation, we would say it's from -1 to 1. Now, this is a little bit different when it comes to your parentheses and brackets. Because of the actual definition of increasing and decreasing and how we relate those points near it, we're actually going to use parentheses for all of these intervals. So when it comes to increasing and decreasing intervals, we will always use parentheses for all of them. This graph is also increasing in that section, so we're going to say union. And then it's increasing from 3 to 5. So this graph is decreasing and then in between spot. So again, we say the interval's there, and that interval would be from 1 to 3, and we're using parentheses for both those intervals. Positive and negative, we're going to list these in a very similar way. It's just asking for a different thing. The positive intervals on the graph is just saying, where is this graph above the y-axis? When are the y values positive? Which would be this area right here. This one we need to be a little bit more careful about the parentheses versus brackets. Where it's exactly equal to 0 has to be a parenthesis because 0 is not positive, it's just 0. So from 0 to 2, that graph is positive. Then that graph is positive again from 4 to 5, but because at 5 exactly that graph has a positive y value, we can use a bracket in that case. Then we look at where it's negative. That would be the areas that we don't have it currently listed. Again, in interval notation, this would be from -1 to 0, and that -1 should have a bracket. And then there's two intervals, so union, and then from 2 to 4, both with parentheses because those are zeros. All right, so let's go ahead, pause the video, and try the next one. All right, so this graph is increasing from -6 to -2, and then decreasing from -2 to 2. That last section there we did not list as either increasing or decreasing because that section of the graph is where it is constant. So if it's not increasing or decreasing, if those y values are not changing, then it's from 2 to 6. All right, now this one, positive and negative, actually a little bit harder because we don't know exactly what those 2 points are. So even though we could estimate it, we want to be able to find those points exactly. So in order to find where it changes from negative to positive, we need to know what that line is. So that is a linear function. It has a slope of 2. And then if we were to continue with that slope of 2, it would have a y-intercept of 7. That means that that x-intercept would be when y was equal to 0, which means the value of that intercept is going to be -7/2 or -3.5. So now we know that this graph is negative from -6 to -3.5. Then it's going to pick back up, and now we need to find what that other intercept is. So again, let's write the equation of that line. That has a slope of -5/2 and a y-intercept of -2. So that means that this graph is going to have an x-intercept of -4/5 or -0.8. So now we can continue writing this interval. Whoops, not -4.5. Let me write it down here. And then it continues to stay positive or negative all the way until the end. That means that the positive interval is in between those 2 points. We already know those 2 points at least. So this is from -3.5 to -4/5 or -0.8. All right, so that's increasing, decreasing, positive, and negative intervals. A lot of this section is probably review from Algebra 1, just making sure, again, we're comfortable with our vocabulary here. So to evaluate f of 2, f of 2 means when x equals 2, what does y equal? So on the graph, when x equals 2, the open circle does not count. It is the filled-in circle that is actually the value. So y is equal to 3 in this case. For that next part, it says to evaluate where f of x is equal to 1. That means when y equals 1, so when y equals 1, x is equal to both -1 and x is equal to +1. Average rate of change is something you've been doing since Algebra 1. That's just another word for slope. But what's a little bit different here now, again, is the notation. This is now in interval notation, which means -2, 0 is not talking about a coordinate that's not listed on your graph. This is saying from the x value of -2 until the x value of 0. So that's saying on your graph, from this point until this point, what is the average rate of change? So all it's asking for is what is the slope of that line right there that I just drew. And that rise over run is -2. So that's the average rate of change on that interval. Yeah, it's all about understanding the notation and how to read it. All right, so the last thing, where is the function discontinuous? So this, a little bit easier to see. If you were to draw this graph, you have to pick up your pencil at 1, and then you have to pick up your pencil again at 2. So this graph is discontinuous at 2 places. What may be a little bit new for you guys is talking about the type of discontinuity. So there are 3 types of discontinuities. There's removable, there is infinite, and then there's a break or a jump. A removable discontinuity looks like a hole in your graph. And what that means basically is your graph still touches both sides of where that little hole is. Whereas a break or a jump looks very different because your graph actually jumps, or you have to pick up your pencil and go to a new y value. You don't just continue from that little open gap. Then the last one is an infinite discontinuity, which you usually see in the form of a vertical asymptote. We're going to deal with these a lot when we get to rational functions. All right, so on example 6, again, pretty easy to find where the discontinuities are. -2, 2, 4, and 6 are all discontinuities. It's not really discontinuous at 8. Your graph just isn't defined at that point. So now we're going to list what type of discontinuities those actually are. So at -2, that would be a jump. At 2, that would be a jump. At 4, it's kind of hard to see on this picture. It's hard to get good graphs on these. Let's pretend those have arrows though. And then that would be an infinite discontinuity. And then at x equals 6, that is another example of a jump. All right, and looking at this last one, again, I'm going to alter this graph a little bit just because it's hard to get these good pictures. So I'm going to make that an arrow. All right, so then here this graph is discontinuous at -1, at 1, and then this one's not labeled. We're going to say that's 2. Now this one has one of every type of discontinuity. -1, that is a jump. X equals 1, that is an example of removable discontinuity, and x equals 2, that is an infinite or vertical asymptote. Now again, you'll notice the difference between these two questions. They both have an infinite discontinuity. One of them they're going in opposite directions, one of them they're going the same direction. It doesn't matter which way they go. What matters is that they are going towards either a positive or negative infinity at that point. The differences between those are going to become a little bit more clear also once you get into calculus and you look at the actual definition and we start talking about limits. All right, so the last big piece of vocab we're going to look at today are even and odd graphs. So a function can be either even, odd, or neither one. So it doesn't have to be either even or odd. The way we test algebraically to figure out which one it is we substitute x with negative x. So we evaluate f of negative x. If you end up with the exact same function after doing it, then that graph is going to be an even function. If you end up with the exact same function, but all of your signs are different and opposite, then that's going to be an odd function. That would look like negative f of x. Odd functions also have origin symmetry, so it's reflected across the origin. Even functions have y-axis symmetry. Y-axis symmetry is pretty easy to see. Origin symmetry is really if you were to reflect it, think if you reflected it over the x and you reflected it over the y. That's what origin symmetry would look like. So example A, so that is an example of origin symmetry. So that would be an odd function. So again, if you were to take this graph, if you flipped it over the y-axis and then you flipped it again over the x-axis, it would end up in the same place, and that is your origin symmetry. That is an odd function. B, that's an example of an even function that has that y-axis symmetry. So algebraically, in order to actually show this and prove this, all we have to do is we evaluate f of negative x. So if I replace all of my x's with negative x, we see what happens. Well, if I take negative x and square it, I'm left with positive x. Negative 2 times negative x becomes positive. Now we compare this to the original function. It is not the exact same function, so it's not even, and it is not every sign different, because even though this sign is different, that first one is not. So it is not odd either. So this is a case where it has neither type, and that's okay. All right, looking at B, so we're going to evaluate f of negative x. So negative x, if I raise that to the 5th power, it is still going to be negative. Negative 2 times negative x becomes positive. So now if you look, this is the exact same as the original, but every sign is different. So that is an odd function. Then our last one here, x to the 4th. If I raise negative x to the 4th power, that would then become positive, which gives me the exact same function I originally started. So this is even. All right, now the very, very last thing, we're actually not going to look at some examples. I just want you guys to get used to seeing this vocab. Concave up versus concave down. Now, a point of inflection, we talked about that briefly. A point of inflection is where your graph changes between concave up and concave down. Again, you're going to see this terminology a lot more when you get to calculus, but we want you guys just to be familiar with it so you can actually identify what a graph looks like that has these things. So one of the easiest things to remember, concave up looks like a cup. So your slope is increasing if it's concave up. So something like your basic quadratic function is concave up, because if you were to take the slope across that graph, each time that slope is getting bigger and bigger and bigger, even as it goes this way, because it's becoming closer and closer to 0. So that would be an example of concave up. Concave down looks like a frown. Okay, the slope is decreasing across that graph. So here's an example of concave down. Again, that slope is getting closer to 0 as it's negative. I'm sorry, as it's positive, it's getting closer to 0 because it's decreasing. And that's concave down. Where your graph changes between the two, so very similar to that cubic function that we saw, that's a point of inflection. So where your graph changes between those two. So I know that is a lot of vocab for the very first day, but we are going to spend some time with this, and you are going to continue to see these things over the course of this unit and the units that follow.